Hello class, let's take a look at example 1. So example 1 deals with a multiple choice exam that has 20 questions, and each question has 4 possible answers. So what they want us to do here on part A is basically evaluate the binomial if you obtain a total of 6 correct questions. Now, you're only using the normal if you're asked. If not, you're just going to use the actual binomial problem. So in this particular case, we're dealing with a binomial problem with 20 questions. Remember that P represents the probability of success, so you only have 4 questions. Therefore, the probability of success is 1 out of 4, and Q is basically the failures, or 3/4. This is in fact a binomial problem, and for any of the binomials that they're going to be asking for a normal approximation, you have to evaluate the following 2 values, which is the mean and the standard deviation. So please take a second and see if you match. I calculated these already just so that we could actually go a little bit faster in the video. So I'm finding sigma is equal to 1.94 rounding to 2 decimal places, and then mu is equal to NP. These 2 formulas are from the previous section, which is the binomial, and they're actually here on the handout. So those are the ones that we will be using if we end up evaluating a normal approximation. Okay, so now back to the actual problem. And in this particular problem, they're asking us to evaluate the probability that the actual subject gets a total of 6 correct questions. So don't forget about declaring the variable. In this case, x is equal to correct questions. And then since they haven't actually mentioned for us to do any actual approximation with the normal, it's just going to be a binomial problem. So for this one, they want exactly 6. So as you happen to evaluate, you're going to run, in this case, the binomial PDF with the following parameters. So you have 20 total questions. Probability of success is 1/4. And they want a total of 6 correct questions. So in this case, the last one would be 6. And remember that PDF for the binomial is used for exact statements. So in this case, 6 correct questions. So please run it, see if you match. So we're getting approximately 0.17. I'm just going to write it as 1686. Which happens to be approximately 0.17. I'll just narrow it down to 2 decimal places. Now we're going to come back to this value in a little bit as we jump to B. But take a second, see if you're matching. You can pause the video, and once again, any approximations within the normal distribution, we're going to have to be using the values of mean and the standard deviation for the binomial. So let's take a look at part B. And in part B, what they want us to do is, in essence, part A, but with the normal approximation. Now, to actually use the normal approximation, you have to follow the chart. And the chart says if you're evaluating an equal statement, you're going to be adding and subtracting a total of 0.5 to the given statement. So for this problem, we're still going to be evaluating the probability of x is equal to 6 as we do the normal approximation. In this case, I'm just going to write it as approximately. Within the normal approximation, this is going to be the probability that x is in between the following 2 statements. So you're going to write it as an inequality. And in this case, it's going to be less than or equal to, so it'll be 5.5. and your actual random variable is going to be in between those two. So x, and then the upper bound, it's going to be 6.5. Now, this is what we're doing. Because the actual statement, it's an equality, this is the category that fits. So if it says equals, you're technically going to say plus 0.5 and minus 0.5. But remember that the random variable happens to be, well, in this case, continuous. So even though it says less than, as we go to the actual, well, as we go to the normal approximation, from 6, you're going to be subtracting 0.5, so that's 5.5, and then adding 0.5, so that's 6.5. Now, as we run the actual approximation, within the actual normal, you're going to be evaluating those two for the parameter. So within the normal distribution, in this case second distributions, we're going to be using number 2, the CDF. So it's back to 7.1, 7.2. The parameters would be 5.5 to 6.5. But remember that the data is not standard normal. So it's going to have to use mu. In this case, mu is equal to 5. And the standard deviation, which we ended up having about 1.94. So 1.94. So let me wait here a minute. Please run it and see if you're matching. Now, our approximation, it's about 0.17. So let me write it again as an approximate. And in this case, the actual calculator is giving me 1786, which is technically approximately 0.18. Now, this is what we're actually doing. With the actual, well, normal approximation, you're estimating the binomial. The binomial actually gave us 0.17. The normal gave us 0.18. So it's pretty decent. And once again, remember that we have to use this chart because you technically have a distribution that's a binomial and whose x values happens to be integers, and then the normal, well, they can be decimals, any number on the number line. As you do any other statements, this is the actual chart that we have to follow. Okay, so let's take a look at problem C. And in problem C, we don't have to declare it. It's already been declared. It's saying the probability that x is less than 5 questions. Now, fewer means less than, so we have to look at the chart. And the chart in here says less than, you're going to be subtracting 0.5. So for this particular one, as we do the actual approximation, I'm just going to write it as this is the probability of x, and in this case, the statement is going to be a less than or equal, and you're subtracting 0.5, so 4.5. Now, keep in mind that the statement actually says less than, so from A, you subtract 0.5. And in this case, they're referring to fewer than 5, so therefore subtracting 0.5 will be 4.5. Now, as we run you have to be very careful for this one. It's now going to be a normal CDF, so number 2, because it says less than, you just need to put a very large negative value, and then its upper bound is going to be 4, 10.5. Don't forget mu, which happens to be 5. And then the standard deviation is 1.94. So I'm actually using again the original mu and sigma. Oops, let me move up a little bit. So mu of 5 and the standard deviation of 1.94. So please run it and see if you're matching. I'm getting approximately 0.3983. And let me give you the code so that you have it. I'm going to pause the video because it's going to be going beyond the time. So let's go to the last part. And in the last part, we're given a statement that says more than 10 questions. So in this case, I'm just going to write it as the probability of x is greater than 10. Now, it just says more than, so you're looking at x is greater. And for an x is greater, you're going to be adding 0.5. So I'm looking at this statement greater, adding 0.5. So for this particular one, we're just going to write it as this is the probability. So it's going to be approximately the probability that x, it's going to be greater than or equal and we're adding 0.5, so 10.5. Once again, we're looking at, in this case, greater statement, you're adding 0.5. So as we run the code, this is going to be approximately the following. So you're basically looking at the following statement. So you're going to be running the normal distribution. So number 2 from 10.5 to a very large value with the mean of 5 and the standard deviation of 1.94. So please run it and see if you're matching. I'm getting that this is approximately 0.0023. And once again, the statement says more than. So on a more than statement, you're basically just adding the 0.5.